Great. So what we're going to do today is we're going to talk about an important topic, equilibrium. And, equilibrium is something economists almost only talk about, solely talk about. We have a lot to say about that as well in mechanics. But before I do, we had a couple of lectures, as it turned out, just on economic surplus. Now it goes to mechanical energy. So I just wanted to know if there were any questions about this. Is it all clear? You guys were able to catch up on it? Huh? Yeah. So it's not an easy topic. So we ended up spending 2 lectures on it. So I think that was worth it one. Okay, so if there's not, what I want to do is get on with this business. All right? So before I even start with the slide, how does an economist determine if you're doing a demand? If you just go to Income 101 and they talk about economic equilibrium. Well, I think they talk about something else. And demand line, supply line, when they cross, they say this is when supply and demand are equal, and this is the price, and this is what happens. And this is just the market price, and everybody's going to have this price, and that's it. That's equilibrium. Now, if you just look at this from a mechanical engineering point of view, this is momentum, velocity. And what it's saying is that 2 objects, right, are in equilibrium if their momentum are equal. Is that true? The answer is no. You know that 2 objects are in equilibrium if the forces balance. If the sum of the forces is 0, that doesn't necessarily imply momentum are equal. All right. So I take 2 objects, this one, and this one. In equilibrium, well, they're in equilibrium when you can't exchange energy between them, but there's no forces acting. All right. So if they're just going every which way, they're going against that, it's just fine for an equilibrium. That's what Newton's first law says. Because when a body at rest goes at constant speed, and if rest is equilibrium, it's just going to maintain its momentum, and nothing is going to change, right? And the fact that another object has a different momentum, that's really fine and well, right? Okay. Now, you say, okay, you're cheating because those are 2 objects that are not in interaction. So now you have 2 agents that are just not trading each other. That's okay. So I take this object and this, and I couple up through a pair. Okay. And then out of that, I can see whether they'll come in equilibrium. Now, suppose I make them in equilibrium. So what's going to happen? When you attach them, they're going to pick up the same speed. And in fact, if 2 objects have the same speed, there's no way to get energy from them because you can't make a collision, you can't do anything. You can't put a spring in between them, you can't put a damper in between them. There's no energy available out of this time. We're going at the same speed. So you need a difference in speed in order to get any type of interaction. Okay? Right. But does that mean that the 2 objects have the same momentum? This object has a much higher mass than this one. They have the same speed. So the momentum are obviously not equal, and yet they're not equilibrium. So you see, this picture you have here just doesn't work right out of the box, okay? I know why they do that, because economists don't have the notion of an economic force like we do, that the force is going to be the change in the price, okay? And that's what we're looking for, is that the price doesn't change. So we're looking for a situation where this is equal to 0. But since this is equal to that, this must mean that the net force is equal to 0. Okay? So for us, the situation is slightly different. So you're only in equilibrium if you if you have no net desires in you, you have a desire to do that, but it's about, a desire to eat more. However, it's balanced by a desire to work less. The two are in balance, and you're just happy the way you are because you want to eat more, but you don't want to work more in order to buy this stuff. Right? So those two desires are equal, and you're not going to do it. Okay? You're just going to keep your price the way it is. Okay? So you got to hunt around for the forces. Okay? So this lecture is going to be about, how do we get from this idea of equilibrium and a free body to this picture? Okay. What is it about this picture how can we explain this? Because we still want to kind of hold on to this idea that this is not completely wrong. All right. It's just not the most general way of, saying that objects are in equilibrium. Okay. So I just first want you guys to appreciate the problem we got ourselves in. So one of the things that can go wrong is you learn everything about economic forces, its desires, and this and that. When you're done learning that, you go, okay, I like equilibrium. You draw two of these lines, you go, here, presto. Can't do that. Can't do that. So what I want to show you is when you can do that. Okay? I also want to show you another thing, is that we do economics, and a lot of Newtonian mechanics is like that too, that if you change the velocity in Newtonian mechanics in one direction, you only change the momentum in the same direction, okay? In economics, if you change the demand for some good like apples, you only change the price of apples, okay? You change the price of pears because they use the substitute goods, okay? Now, the answer is sometimes no and sometimes yes, all right? So here's another issue we have to confront, okay? Namely, how is the coupling between velocity and momentum and demand and price? And how can we couple this? So we have to go a little bit outside of Newtonian mechanics, because in Newtonian mechanics, all directions are considered orthogonal. But it's not a big excursion, and then we can explain that. And then we'll come to a more vectorial treatment here. It's not a simple law of demand where you have one good and one price, but you have two goods and two prices, and they're related to it with a tensor. And with this tensor, we can calculate the cross elasticities and the substitution effect and things like that, and we can represent that. Okay? So that's the other topic I want to address. All right? So first, just understand these are non-trivial issues we now have to get over with. All right. So that's why they narrowed their own chapter in this paper. Okay. Because basically, after we did energy and surplus, we were done. Right? Walk away. All right. Now, interestingly enough, Marshall came up with this idea of demand and supply lines crossing as being equilibrium. It's quote from his book where he does that. He says the simplest case of balance or equilibrium, so he equates the two. It's not completely clear because a balance is not always equilibrium, all right? Because you can have a balance and still things are accelerating or whatever you mean by equilibrium, but that's okay. Maybe he means right here. Between desire and effort is found when a person satisfies one of his wants. Okay. Now, what's interesting is with the background we have now, we can totally decipher what he says. Okay. So a desire, that's a force. Right? Okay. It's just the opposite of a desire, right? Maybe an incentive. So it's a force acting in another direction. Here's one. Well, this is maybe this guy. Right? Okay, the effort. Okay, is found when a person satisfies one of his wants. Okay, now this is about power. So for us, a want is the same as a desire and effort, and satisfying this want is to multiply it by the demand, and then get the amount of power you get out of it, which is the rate at which your surplus is increasing. All right. So you see this sentence is a little bit scrambled, but all the ideas are there. So he obviously means here. Oh no, how do I?
De pen uitzetten eerst. Ja, maar nu staat hij nog op tekenen.
Ja, dus ik moet uit de tekenen springen.
Voor mij een knop aan de zijkant? Iets. Had een trucje voor me, maar ik ben het vergeten.
Ja.
Dus ja. Ja.
Nee. Dat is gewoon, dan moeten we even opnieuw starten dan. Oké. Zo. Yes. So you see, all the ingredients are here. There's this idea of a three-body diagram, right? Which I drew over here, where equilibrium is something where the forces balance, okay? The desires and the efforts. And there's the idea of dissipation. That's the power of the dissipation. Huh? Okay. Now, those ideas are important for us. So, when the forces balance, we would often say the system is at rest, right? So it's going at a constant speed. It's not necessarily in equilibrium yet. It still has got speed, so it's still changing its position. Right? How do you get it to stop changing your position? That is to take out all the kinetic energy and dissipate it, right? So you attach a damper to it, or you put some friction to it, and you'll see that, you know, the momentum will keep decreasing, and it will end up at zero, and your position will be what it is, and it won't change either. So for both, the momentum and the position will change, okay? So there are two steps to equilibrium. First is what I would say is rest. That is going at a constant speed. And the first is full, equilibrium, where not only does your momentum not change, that means going at a constant speed, but also your position does not change, okay? Those are the two ingredients here, okay? So, if we summarize that for what it means in economics, rest is a situation, and that's what Newton looked at, where the price is not changing, okay? We may call that dynamic equilibrium. There's no good name for it. Newton calls it rest, huh? Body at rest. That doesn't mean a body standing still. It's at rest, okay? See, you gotta understand the brilliance of Newton here, that he makes a distinction between rest and standing still. Because before Newton, the Aristotelian science had it that equilibrium only could be if the thing is not moving. If it's moving, something has to push it in order to keep moving. And you might think that's the case if you live in a world of friction, right? But it's just not the case. If you take away the friction, the thing will keep moving by itself, okay? And there's laws that warn you about this, all right? But there's the second law, that is actually the second law of thermodynamics that says that entropy will always increase, right? So you will always have some type of dissipation. That law makes sure that also your position won't change, okay? And the same is in economics, okay? So price equilibrium, what economics mean by price equilibrium is a kind of Newtonian rest, is that you just keep demanding some amount of goods all the time, okay? So your price is not changing, but the amount of goods in storage may go on indefinitely, all right? That be, that's just our assumption. You don't care about the goods, no scarcity, you're on the friction getting them, so you just keep going, you know? Get all this air, you blow it out again. Now we're not talking about the oxygen that you use, but you know, all the nitrogen you blow in, blow out, you don't care, right? right? We don't keep, right? Okay. So this situation is often what we may refer to as static equilibrium, full dynamic equilibrium. Huh? And I think competitive equilibrium is an economic thing that comes the closest. And we'll talk about that why. The idea, of course, is that the competitive equilibrium is when the entropy is the biggest, huh? So that the profits are all distributed among all the players because they're in competition. And profit, as you know, that's the energy is distributed among all the particles. And there's nowhere else to go for the surplus. All right? So this is the idea. And interestingly enough, it's already present with Marshall, but it's not really developed any further. Actually, you see later in economics they move away from this idea of forces and and it becomes way more mathematical. Okay. Yes.
So I can imagine that price equilibrium is sort of what you as a consumer experience. Like you demand a certain amount of bread each week.
Yeah.
You pay sort of an equal price for that.
Yeah.
Is there also, and then the competitive equilibrium is more like on macro scale,
Right.
I guess. Is there also an example of competitive equilibrium in our daily lives as a consumer?
Yeah, because outside that, you're really not. I mean, what you are as a consumer is you consume the stuff. You don't just buy it and just do nothing. That's what you do with, say, nitrogen. Nitrogen is in the air, and you breathe it in, you breathe it out, and you just do nothing. And with food, apples, that's certainly not the case. I mean, that would be the case if you would buy these apples and just throw them in your storage and you don't care, right? But you don't do that. You process them, right? And it gives you energy, and you can work, and you can make money after you made this apple. So actually, a very complicated process is going on with all kinds of forces, that are such that at a certain point, this will be zero if you have enough friction going on. And these are transaction costs you have or other irrecoverable costs, you see? So you have to see yourself not as a simple demander, but as a very complicated system with all kinds of junk, okay? That's what you got to do. So this demander, that's really a very simplistic view, all right? Now, when an economist thinks of demand or a consumer, he will draw this line. What happens to the surplus? He will assume this is welfare. We'll talk about this later also. So that it gets dissipated, so that he's actually consuming. That means that, mechanically speaking, that he's got some kind of damper, that he just turns all this into heat, feeling good. Right? But you can also imagine he's using this to do an investment and then get it out later, put it in storage and then he can eat these apples later, but then he won't be this, then you will see his price going up and down if he uses a storage, right? So now he's more of a trader, okay?
Yeah.
So I think the answer is more a consumer or producer, all these things, they're very complicated. And it's the same, that's, mass. I mean, you can think of your car as a mass, but really it's a very complicated thing with turning wheels and pistons are going up and down. So the model of it just going at a constant speed is very simplistic, right? If you're going on the highway, even then you have friction and pushing the gas pedal and there are all these forces acting to keep this thing at constant speed. So it's more of a comet, without a gravity field. That's what this is, right? Very simple system. All right. So don't confuse this with a consumer or a real economic system. So if you think in the endpoint phase, you have to think a whole block like this and all kinds of junk in here, right? This is the way you would do it. So there are no pure masses and no pure anything. Okay. Okay. But thank you. That's a good question because it's easy to fall back and okay. Yeah. So this agent is what I call a demander. All he does is demand stuff. Right? The rest he doesn't know what he's doing with it. All right. Huh? Part of this exercise is to is to think of economics in terms of these really simple agents, right? Ridiculously simple. But mechanics is to start thinking of a complicated structure composed of these really ridiculously simple elements who have one constitutive law, F is M times A, or F is K times Q, or whatever you want, right? And get good at that, right? So I wanted to talk a little bit further about this idea of equilibrium. So this was what Marshall had to say, and to make the connection. Smith also has this idea of equilibrium price. So I'm now talking about this thing here, right? Okay? And his idea is that ultimately, look, but economists are always looking for its price stability, so that this thing should be zero. So he had already ideas why this would happen. And I have these quotes in the paper, but they're good to talk about. Mythical is not the equilibrium price, it's the natural price. Okay? You know, so it's a little bit Aristotelian to think that way, because Aristotle, he thought there was a natural motion of every element. So that some things just fall at a higher rate than others. So feathers fall kind of slow, bricks fall kind of fall very fast. Fire kind of falls negatively, right? The smoke, right? So he had this idea that everything had some kind of natural momentum associated with it, Aristotle, which is wrong, of course, because gravity just same acceleration to everything, right? It's just a friction force that messes you up. Okay? So before Newton, Aristotle's think was about the natural, the natural momentum. You see, Smith is thinking of this way also about a natural price, I think. But what you've got to see is this natural price is just some point where it doesn't change, okay? Wherever that may be. All right, is where the central price. So we talked about the central, to which the prices of all our commodities are continually gravitating. So he uses a gravity thing, right? Just like Aristotle. So you have this thing of gravity, and it's keeping everything at its natural momentum. All right. Different accidents may sometimes keep them suspended a good deal above it, sometimes below. So the smoke may go a little left, it may go right, a little up. But on the average, the smoke really just does this, the brick does that, right? But then they continue tending towards it. So there is this idea that everything tends to some kind of situation where this is zero, right? Okay, that's kind of built in here. See, that's also what Aristotle built into his thing. So everything tends to acquire a constant velocity when it's falling, not when it's moving sideways. Then the velocity naturally will always be zero, right? Because everything stops. Okay, but this way there is this natural thing. So this was a wrong picture of Aristotle, right? So, but Newton people were able to explain it in Newton's theory. They just said, well, of course, it's accelerating. However, if you look at air as a friction force, and at a certain point, those things are equal, depending a little bit on the shape and the disk. And you do all these complicated calculations. I'm sure you've done it in fluid mechanics or whatever you do, and you get this thing called the terminal velocity. I don't know. And then all of a sudden, you have this natural velocity. I mean, whatever. Okay. It's good to think through these things, how this thinking evolves, all right? Marshall says the following, right? So Marshall is a lot later than Smith, right? So with Marshall, what Smith wrote, I think Newton was just done writing or not yet. It was around the same time, okay? Not quite sure whether Smith was before or after Newton. But, you see this. Ideas of Newton and force are not really prevalent in their thinking yet, more the Aristotelian ideas. But now if you read Marshall, you see that Newton changed the whole thinking. Now, Marshall is 19th century. right? So then everybody's thinking Newtonian, everybody's building machines, everybody knows what force is. When demand and supply are stable equilibrium, so it talks about stable equilibrium, in any action that you move it from a equilibrium position, you'll be instantaneously brought back by forces, right? So you see the thinking is already different. Then to push it back to that position. And the position he just means economic position, right? Whatever it is. Just as if a stone hanging by a string is displaced, so he thinks of a pendulum. You see that? It's displaced. You know, the force of one has to bring it back to its equilibrium position. This is the idea. There's another confusion. So you see, he starts thinking completely Newtonian. He doesn't really get that because doesn't really do this. I mean, if you take a pendulum or a stone from a string, you do this, will it bring it back to this? No. Suppose there's no friction, what will happen then? Just keep going like this. It will never get. So this is actually wrong. Okay. So his whole idea that you're going to go to this crossing of the two is not right. You know, an example, he's got to put some friction in there in order for this to be true. At present, it said once. Okay. But he has to say, it brings it back, but it will overshoot, you know, so it gets it back. There's a restoring force, okay? That's what he needs to say. Okay? He's a little bit sloppy here. We're going to analyze this statement, okay? Let's see what the real answer should be and how you can get it. See, he's not dealing with dynamics. He's just dealing with static, and he's just going like, okay, maybe it will flop around a bit, but ultimately it will do that. So what is the ingredient that makes it sure that ultimately he'll get there and he will stay in the equilibrium position? So he wants friction. So the balance of forces is not going to be enough. You need a friction force. Okay? This friction force is what I like to think of as the invisible hand. Now, this is the most misquoted thing of Smith and Smith didn't mean what not saying he means. But I think the idea now is that Smith's invisible hand is a sort of a metaphor for that market will always tend to an equilibrium, right? Find an equilibrium place, okay? And that is in this invisible hand, and we can't see where it goes, all right? So if it's going to tend there, it won't be look, what is a hand, right? What does a hand do? You grasp things, but basically what you mean is pushing. So it's applying force. So this must be some special force if you think of it as a hand, right? Okay. So what is this? Well, what he really said was that down there in the wealth of nations, he said something else in another thing that I quoted in the previous led by an invisible hand to promote an end which was no part of his intention. So he's saying this agent is doing whatever he feels like doing, but through the interactions with all the other agents, you know, he's going to bring everything to an equilibrium. But he never intended to do this. It just happened. All right. That's what he said. That's his picture. Now, how do we translate that picture to mechanics? Let me give you an idea. Suppose here's an agent. And he's doing something. He's demanding so many of this and so much of that, or demanding that, supplying that. Here's another one doing that, right? They're all doing that thing. Maybe they're connected through dampers and other things, and they're going every which way, right? And they're connected to springs. What's going to happen? Suppose they all start off more or less in the same way, and then they start bouncing around. So this one goes like that, and they bounce against each other. What's going to happen after a while, right?
It dissipates.
It dissipates. And they're going every which way. what's going to happen. Now, let me ask you this. Did any one of these particles intend to do that? Did he say, well, hey, I'm not physical? Of course not. This is going every which way. And we say we cannot keep track, and this is such a chaotic system that we are incapable of keeping track of what's going on. So we just look at the average kinetic energy, all right? It's all dissipated. So if all the particles started off, going the same direction, this whole central mass will be moving, but after a while, it's like, stand still, or it's just getting hot. If you touch it, it will get hot, right? That's what you feel, is just the particles hitting your hand, right? That's heat, okay? That's a high temperature. So that's the picture, right? So this thing will start moving, right? The central mass will start moving. The movement is all inside. So this is really that picture, right? So if this is an agent, and if an interaction is a trade, right? A collision, but this is what happens. Okay, this guy has this. They all have the same stuff, but one is a little bit more bananas, so he can trade with this one bananas, and the other one also have bananas, and so just little deviations allow this thing to spread out all the goods equally among each other on the average, right? And therefore, spread out the surplus, okay? That's what happens. This is what we call entropy formation. Right? Now, the economic friction, we had a formula for, and we represented by this damper. But what happens in this damper? Well, suddenly you have everything going one direction. There's a little hole here, and you push all these little particles through, and now they're going every which way, right? So it's one way of turning surplus all directed to buying the same good to buying two goods now and spread out over multiple agents. And this agent who we're here, say here's the math, we lost everything, right? Not everything, because he's still bouncing along with these guys with the same little fluctuations, okay? That's the picture. So you see this picture of an invisible hand is really one of friction. This is the process of friction. Friction is the generation of entropy, and why is that dissipation? Because you take the energy and you distribute it out over all the degrees of freedom. That's the idea. Huh? Okay? Is that clear?
Yeah.
Huh? That's what happens. You see that? I see you nodding, so I want to.
It's like that way of thinking about fiction is like fine.
Yeah, that's why I call it economic fiction. Okay. And what is this entropy then? It just says how it's all spread out. So that is, if it's among agents, you would say the surplus or the profits are, the surplus is well distributed. It's just when distributed, it's not at one person. So one person has all this Apple surplus, and what he does in trade is you get a little bit, and he gets a little bit of your surplus, and then we all spread it out. That's why the thing works, okay? Now there's an amount of distribution, and so if you distribute it among agents, we call it distribution. If you distribute it among different goods, we call it diversification, okay? And in general, you can do both. So if you have N agents and D goods, you have N D dimensions to diversify. Okay? If you have both price and position, you can actually add it too. Right? That's the detail. So this is your diversification, and this is your distribution. And the degree in which you've done that, that's your degree of diversification. You see? Now, we all know that what you want, or what everybody tends to, is to diversify as well as possible. You want a well-diversified set of goods. You don't want just apples, you want pears. That's what you call wealthy. Okay? You want a portfolio. I don't only one stock, I want all kinds of stock, as much as I can. That's a well-diversified. So we tend to increase the amount of equity in the environment, in our economy, by giving everybody an equal amount of the surplus and the diversification per person, per capita. So what we are saying here is that if we measure that degree using entropy, then it's natural to think of the increase in entropy as the tendency for people to diversify the surplus. Okay? And this process is exactly this. Okay? So there's a lot of guys, the girls who use entropy and energy and economics, but it was all a little bit, from a high level, right? So, well, I think this is economic entropy. And the nice thing of economic engineering is you can do it using statistical mechanics. You can really look, what is this agent doing? What is this doing? And what are these processes? And now I know exactly, I don't have to call it economic. I can call it diversification. I know economic diversification or economic distribution, whatever it is, right? And that together, we call it dissipation, all right? We also know that this is always increasing. It always has to be positive. The amount that you know that the amount that you're dissipating in surplus always has to be positive, because you're not going to de-diversify. That's nonsense, okay? At least not voluntarily, if you just kind of. So we know that ultimately the invisible hand will imply, well, the second law of thermal will imply that everything comes to a full stop and price and stock equilibrium are attained, right? Okay? That's the big picture behind this thing. All right? Now, the way it does, it's good to make a distinction between just stability. This is like, I can call this more marginal stability or something. I don't know why I put it in front of it. And what we call asymptotic stability or Lyapunov stability or whatever you want. Okay? So, scarcity, that's the thing that Marshall's talking about, right? So if you're away from equilibrium, right, and the goods are scarce, the scarcity is going to pull you back, all right? So really, the scarcity force is a restoring force. So it's the negative of the scarcity force that matters, right? So that's what we say is also the convenience, okay? So what you're going to see is that when you've got a lot in storage, you really have an overabundance. So it's going to, the direction the price increase is down. It goes in the decrease, the price is going to decrease. So it's in the opposite direction of the abundance, right? Of stock. So it's a restoring force. So you're trying to go back to that situation where you're force free. Unfortunately, with just scarcity, you're always going to shoot, because once you're at the point where you have no scarcity force, you have so much inertia, that there's so much demand that you're going to over demand, over so much supply, you're going to oversupply. So you're going to be low. You're going to be low in stock, and then you have to go back again. So you get this cycle that you go through. Okay, there's no way around that. This is in itself not so bad, because the pendulum, the only thing it knows how to do is find equilibrium like this. It can't do any better than this because it can't generate entropy. All right? But the only way a pure trader, a trader who doesn't have any losses, knows how to do is this. I mean, he's got to stock up, then and then he has to, he has got too much, he's got to lower his price, and he has to stock down. So his inventory is going like this. And his price is like a half degree on phase, right? That's all he can do. That's all he can do. All right? So that's what you see also. Go to a dealer, you'll see his inventory going up and down, and his price going between a bidder, maximum and a minimum, because he's buying and selling,
It's a little bit nature's version of the PID control.
Yeah.
You got a proportional one that's just putting it back. And then the differentiator, that's the friction.
But why think of it as a control thing? You can just think of it as a spring match system. You know, well, why a controller? See, he just happens to have an inventory and he has demand. And if you will put that together, right, what are you going to get? You're going to get that M Q doubled up plus KQ is 0, right? So you can see, this is the stock. You know, this is the extension of his demand. You can also write it like this. So what's the solution? This is what it's going to do. Why think of it as PID control? It's just somebody who only has storage and only demands will end up going through cycles. That's all he can do. That's the best that person can do. Why? Because he has no way of dissipating it out. Okay? Soon as you add a damper here, then the situation is going to be different. Then he may do this, conversion equilibrium, or he may what it is, or like this, right? When he's critically damped, yeah? Or he may be overdamped, and he takes off like a maniac and goes very slow, right? Yeah. All right. You get all kinds of other, you learn all these, right? So think of it as a second order system, marginally stable. So if you look at these Lyapunov stability things, you'll see that if you start off from a position of certain amplitude, it will stay in there. It won't necessarily go to 0, right? That's all it's the same. If you do nonlinear, it's like the center manifold, or if you do linear, it's like you're having your poles on the y-axis. And the stable systems are the ones where the poles are on the left side of the plane. Unstable systems, you got to put energy in. So you got to put circuits in. It has to come from outside. Then you're talking controllers, because the controller does that. But these are just systems that just go by themselves. Okay? All right? So this scarcity just works counter to the demand movements, just like a spring is always working counter to, that the momentum. It's trying to reduce the momentum. If your momentum is big and you've got a lot of stuff, it's going to try to bring it down, right? Then it will just go up and down like that, right? So that creates stability. Otherwise, the thing is just going to fly off, all right? The second thing is when you get asymptotic stability. So this will be in our parlance when you're on the pole, when you're a linear system, the poles are just going to be on the left-hand plane. So everything is either going to look like a damped sinusoid, or if it's a second-order system, or some over-damped thing, all the poles on the real axis, two coincident poles. Huh? That happens because friction is an impeding force, right? This is a restoring force. So this thing is minus KQ. I just wrote it quite general, right? What's important here is this minus sign. This is a quadratic form, so it points the other way. And here also you get a minus sign, okay? So if you have a velocity, it's going to impede that velocity, right? And the price change is going to be proportional to the quantity demanded, all right? And the cause of the proportionality is precisely this. Now, you know that the quantity demanded is equal to the price divided by the price inelasticity. So if I fill that in, I'll get this thing, and this is the damping rate, and this is B divided by M. So that's in 1 over days or something, 1 over time, right? So you see another way to look at it is that these frictional elements, they start to discount watts per unit of time, right? Okay. When is this P dot zero? Well, obviously when V is zero. Okay. So from this, you'll see that the surface is conserved, right? So with a spring mass system, the energy is conserved. We would say the surface, all we're doing here is when you have a storage, is you're moving the surplus from active direct surplus into indirect surplus. So you're just moving the goods into your storage and just later on selling it, just keep moving like that, I mean, it's kind of pointless, but that's all you know what to do. Because you happen to have this thing, that's just the optimal thing to do for you. How that you can maintain on the average some kind of demand, all right? In this case, you'll see that because of dissipation, you know that H dot is going to be equal to that dissipation, right? So H is the total energy, right? Mechanical energy, so kinetic plus potential, and the decrease of that is going to be equal to the power, the dissipated power. So here it's saying that the total surplus gets allocated to consumption at this rate. Okay, this is what we call a consumptive allocation. So that could also be part of a consumer, right? It's not only has the surplus, but also consumes it as soon as he gets it. All right. And if he doesn't reintroduce more surplus from somewhere by working, and this is going to die a miserable death when he won't be able to consume it. Okay? He is gone. His prices are all nowhere, and his demand is gone. He's just out of the market. It's sad. All right. This is a little bit what the ancients said. Now, that is these fundamental theorems of welfare economics. Okay, and there's two of them. I never really understand what to say, but I don't think that's necessary because we just want to see what they mean for how they fit into our analysis. Okay, so I put in one sentence what they say, but it's very hard to get it in there. So they say the first one says economic equilibrium can be attained by every Pareto efficient allocation and inversely. All right, there's a Pareto efficient allocation for every economic equilibrium. Let me first tell you what I mean by Pareto efficient allocation. You know this? Does anybody heard of Pareto efficiency?
80-20 rule, right?
What?
The 80-20 rule.
No, that's not like it. The prisoner did not.
Best strategy.
No, yeah. So no, that's not it either. Yeah, that's different. That's also from Pareto. That's the guy, Wilfredo Pareto. It was Wilfred Pareto, Wilfredo, he was an Italian guy. He did a bunch of steps. A Pareto efficiency, you can look it up. And the idea is that a market is Pareto efficient if you cannot make one person better off without making another person worse off. Okay? So you could easily imagine a market where both people can be made better off. You have 100 apples, I have 100 pears. If I give you 50 pears and you give me 50 apples, both of us are better off. So what's the idea is that the surplus is not distributed evenly. I have a lot of surplus in pears and you have a lot of surplus in apples. And what we need to do is distribute that, okay? So mechanically, we say the situation is that my kinetic energy is all in the x direction, your kinetic energy in the y direction. If we start bouncing against each other, we'll end up approximately, as a sort of billiard ball, approximately both on the average with just as much x kinetic energy as y kinetic energy. Okay? Now, when is a market period efficient? Is when you cannot do this anymore. Right? Now, when can you not do this anymore? If you think of the mechanical situation, there's no way, if you're going, and I'm going slow, I can get energy, the traders say, energy out of this by making you go at the same speed. I just hold myself together, and I make a little engine there, and you go, and then you end up going at the same speed, right? So I put a little dynamo there, right? A little generator. Can you imagine that? Right? And then I can take out the surplus kinetic energy when you're going at different speeds, right? And this is also true if you're going this way and you're going that way. I can put a little gear and I'll slow this guy down, so that guy and they go in the same. Once you go in the same speed in the same direction, there's nothing you can do anymore. No collisions. No, you can make no interaction. Okay? All right. Now, suppose you have this box full of all these particles. They're going every which way. There was a guy called Maxwell. He's extremely intelligent guy, and he came up with this idea of Maxwell's demon. Has anybody heard of this? Maxwell's demon.
Yeah, I think, but I heard here.
Yeah. So he says, listen, this whole idea of entropy, it doesn't make sense to me, and this is the reason. Is suppose these things are going every which way. Now you're telling me that because the entropy is maximal, it's in thermal equilibrium, there's no way I can get energy out of this thing. I cannot just pull some heat out of it. Okay, that's what the second law tells you. Right? Now, suppose I do the following. I have this little guy, you call it a demon, like a devil, he's sitting there, and as soon as he sees a little particle going this way, he'll let it in. And if it goes slow, he doesn't let it in. And the other way, he lets out the slow particles or something. So he's going to, after a while, by spending no energy, he's a little latch, right? Spending no energy, he's going to get all the fast particles there and all the slow particles there. And he had a uniform temperature before, and now it's really hot here and really cold over there. How's that possible? Because we all know that if the thing is uniform in temperature, there's no way we change the temperature distribution, right? So what's wrong here? Well, there's all kinds of things wrong because the problem is the demon needs information in order to do that because he's got to find out that, he's got to keep a record, this guy's going fast. And that information he's got to write on his hard disk, and that hard disk is getting hot, okay? And the process is getting hot, and that he's exactly the same as what he's thinking he's saying. So you won't get out of it. Okay, but the point is a little bit different. You can turn this thing around, and I think that was there's all these formulations of entropy, and I think that was a German researcher with a Greek man. I forget who it is, but he took this, and I believe this case, as a definition of entropy, as thermodynamic equilibrium, impossibility of the Maxwell demon. Demon is also called the PPM2, a perpetual motion machine of the second kind, because you can create, you can destroy entropy, right? These are interesting because suppose you have a ship and it's going on the ocean and you have all this diesel with you and there's, they pop it into the ocean and then the ocean gets a little hotter. Now, wouldn't it be nice if you just could take that heat out and put it back in the ship and they're going, let's keep going, no problem. You don't need any energy. Very desirable boat. Or it puts all this heat in the environment, but just take it on again, right? All right? So friction only goes one way, you can't get it out. So,
well, you can get it out, it costs more energy than.
Yeah. The same.
Yeah.
That's the problem with the demon too.
Yeah, so the demon will always cost more energy to operate.
They're the same.
Oh,
Exactly the same.
exactly the same.
Right. So
That's worth it.
that's the point. At that point, it doesn't come. Now think of Pareto optimum. So suppose this thermodynamic system is not in equilibrium, right? So you have these two boxes, this one at one temperature, this one at another. You can build yourself a little Carnot engine and just get some work out. It's no problem. So this thing is obviously not in equilibrium. Okay. Now suppose this could, and after a while these temperatures start equalizing at a certain point they are equal. What do you notice? Well, you notice that this thing becomes zero. Okay. So you can turn this around. You can say, well, this is zero, then this must be an equilibrium. Okay. All right. Now, how you can think of Pareto efficiency. So you think of this thing, say two economies. Here are Bush guys, here are usually people, right? Huh? And you are a trader, and you're going to try to make both better off. Well, you're going to succeed because the temperatures are different, right? You know, so you're going to be able to do transactions. But there comes a moment where you won't be able to take the middle here in the trade, and get the surplus out. That's the moment. Okay. So you can't make both parties better off. But also make worse off, and he won't allow it. Fine. So you can think of Pareto efficiency as some general economic equilibrium. You see that? If you do that, you can reread this and say as a statement of the second law. Okay. So Pareto efficiency just means, it's in thermodynamic equilibrium. Okay. Means this economic equilibrium and this gradation is thermodynamic equilibrium, right? So if you look at these US diagrams, I don't know, guys know that. Here, you can have some kind of energy, they're all here, and different levels of entropy, and then you could go up here, and then at this point, it's all over. So these are all the Pareto optimal states, and this is Pareto efficiency. Okay. Now, how do you go to here? Well, that's the process is called friction, dissipation. All right. So energy is conserved. However, you generate this entropy. All right. Okay. You can also do this. Drop down here. You also have equilibrium. That's what that trader does. Huh? So he just takes out the surplus that's in there. He doesn't what Carnot engine does. He doesn't take out the surplus. You don't generate any entropy. All right. So you can reread this thing as a statement of the second law. All right. And statement of the second law is that equilibrium coexists, right? So there always is an equilibrium. And then you figure out that entropy must be that measurement factor of how close you are to it. All right. Okay. There's a second one. It says any efficient allocation you can achieve by redistributing the resources. So if you're not happy with the way it got into equilibrium, you just kind of change some stuff around and you're going to get a different equilibrium. Okay, that's what this is saying. I don't really put much interest in this because this is just playing around. This is the interesting one. They get really interested in this because this justifies using government intervention to take a whole pile of surplus and dump it somewhere else and let somebody else, let somebody else get hurt. Yeah? And then sure enough, you'll get some other equilibrium. This is the interesting thing. Now, all this is only possible using statistics, this kind of reasoning, only using statistical mechanics. So thermodynamics, the way you guys learned it in the first year, it's just macro. So you just say, hey, temperature is just this. Entropy is this. And nobody said, hey, temperature is what you feel when all these little particles are hitting you and stuff. Just say, pop, there it is. And I wondered why you put a thermometer in there. Okay? This kind of business is called statistical mechanics, and it was done by Boltzmann and Maxwell and Gibbs. And it really clarified why entropy exists and what the mechanisms are. And then later out of that came quantum mechanics. Okay. Now, statistical mechanics uses Newton's laws that look deterministic, but in the end, see, this was a big dilemma they had. Like, how can Newton's laws that give you these deterministic things where time can go either way? What do you care, right? If you have this oscillator and you run it backwards, you're not going to see anything different. You're not going to look ridiculous. You know, if you make a movie of an oscillator, you can run the movie backward. But if you have a movie with friction, so a child will swing, the swing is going to be okay, but a hair that flows forward or something is ridiculous, okay? All kinds of things are ridiculous. Like you cut a melon into, and all of a sudden with your knife, you can put it together, you know? So that looks ridiculous, okay? And the question was, why can laws that really are purely deterministic nevertheless cause things that are, it's one direction in time. You can't work your way back anymore. And this was kind of the answer to that. You start averaging so much that you can't really see anymore what's going on, because it costs more energy to go figure out what the determinism is than you get from you know, so it's hopeless. Not just because your computers are not good enough. It's just hopeless. You know, it's just hopeless. So there you have a fundamental thing. So it was a big thing. And I mention this again because a lot of economists will do thermal, but it's all at the kind of pressure thermal level where you just see, if you do thermal, it just feels like it's unrelated to those. You know, you first get statics, then strength of materials, then dynamics, and then thermodynamics, right? And the first three are very related. Right? Forces, position, blah, blah, they build on each other. And the last one, no relationship, just totally different. All concepts are different, everything different, right? So that's weird, right? Something weird. That makes thermal also so understandable. What am I going to do with that? I apply, well, I can build a heat engine, but how does it relate? Okay, and this is what was figured out in the 19th century, or people like Boltzmann and Gibbs and Maxwell. Like, what is the relationship? And then it's an averaging function. This is what we leverage here in economic engineering. Right? So we look at friction really as fundamentally an averaging kind of thing. And also at this invisible hand. All right. Okay. It's the shoulders of giants we're standing on, because it's a very difficult matter to figure this all out. Very. I don't even think it's still figured out yet. So now put it to okay, so this is good, right? So you see there's a big difference in these ideas of equilibrium, whether it's stable, you must have friction, or when it's not, and then maybe you need a restoring force or something, right? Okay, so now let's look at this side. This is how Marshall ended up creating his equilibrium. So after all these quotes and everything, it's more theoretical. Let's take an example where we actually get equilibrium. So on the right, you recognize the typical thing you learn Econ 101 at your high school or secondary school, whatever you want to call it. And on the left, you see what we will call the two-blind problem, right? That means there are two masses. Attach them to each other through a damping, all right? So I put demand in there, and there are two demanders. Actually, there's one supplier and one demander, and I put a little bit of market friction in there, right? So they are interacting with each other. So this is the quantity demanded, this is the quantity supplied, and this one is bigger than that one. Therefore, this one is the net demander with respect to that one, supplier. This is the net supplier, although you may think that both positive, that doesn't matter, right? Yeah. And what are the other ones? Interacting. Who is intermediary? Who is intermediating the trade? You know, and what's going to happen after they interact? These two velocities or these quantities will be equal. If you look at the system, you know, they're maybe going like this. This one at a lower speed, the other one at a higher speed. You know that in the end, this is going to go, it's going to pull it in and go with the same velocity. All right? So by looking at this, you know what's going to happen. So the momentum of this guy is going to increase, the momentum of that guy is going to decrease, right? Okay? And then at a certain point, and how much of this is going to increase? Well, this is going to decrease by force minus F, and this by force F is going to bring it up. Now, force is mitigated by this damper, the link, right? Okay? So this force balances that force, right? So this is the actual force, of whatever you want to call it. Okay? All right? So the other thing, let's just analyze this thing first mechanically. So if we put a box around this thing, then what do we see? Well, there's no external forces acting. So what's going to happen to the center of mass? It's right here. Okay. It's going to keep the same velocity, right? So you look at it from the outside, they maybe have different velocities, but the center of mass is going to get almost. So that's the third rule disturbing all this. So the action-reaction pair, they all have. Okay? And here you see that it's only this and this person, they're trading within each other. There is no big, there are no other agents involved in this trade. All right? Okay. The other thing that is missing here is normally what we will draw as some inertial reference frame. You know, that has a velocity and a zero, and then we'll just do the analysis with respect to an inertial reference. Well, we don't have this here. Okay? So what do? You don't have an inertial reference. Because you know that this is a constant velocity, what you can do is you just attach the frame to the center of mass. Okay? Now, maybe going at some amazing speed, right? But you don't care. It's a valid inertial frame. Okay? So for an observer, for this thing, it's very clear that this is a negative velocity and this is a positive velocity. Okay? I do this for this observer, but from here, this one's lagging behind, this one is running ahead. Okay? And the difference in velocity is really the only thing that's of importance here. Okay? And I have that on. All right? Okay? Now, well, let's go and let's okay, so everybody sees this is what's going on, right? If not, you could easily calculate what's going to happen. Now, this is an economic picture. All right? So this is just some frame here. I just drew that with respect to this one, not this one. I have another one. So what I'm going to do is I'm going to take this demand, this is what I call the aggregate demand, 0. Well, put my initial reference frame here. Okay. I'm going to take the momentum price here. I'm going to take the price divided by 2, and I'm going to put that over there. Right. So, what do I call this? This thing I call the aggregate demand. That's going to be the zero velocity. Okay. Say PCM. If you look at this is what the economists or traders will call the midpoint. So it's the price exactly in between. Is that is half the distance of the price interval between these two. Okay. Right.
So should there be a halt in the graph in front of the PC or?
Yeah, I think so. I've come down on that, but I think there should be
Yeah.
it's going to be 0, so it's all going to make no difference. Right? This is the thing. And the other problem I had was that the dumb way these economists draw it is that this thing ended up being actually twice the midpoint price. You know? So it's twice the half of that. It's not even that. It's a good point. When I was reviewing this for the lecture, I was thinking, yeah, well, what was that? But then I remember I sorted it out that in this dumb graph, this is actually this. And that this is what an economist might call, a trader might call the midpoint price. Okay? And the difference in the momentum, that's what he calls the bid-ask spread, right? So the demander, he bids, the supplier, he asks, and the difference of momentum is the bid-ask spread. In between there is this midpoint price. Now we take the midpoint price to be the 0. Okay? That's the setup. The following? It's a lot of little details, but it all makes sense in the end. So now we're in business. Then we can say, all right, we'll plot the demander, we'll plot it over here. It will be right. I'll plot that going left. So you see, that's really what I did. And the supplier is right. So you got to flip this way. So what I did was, you see the demander's quantity is running left. It's a little bit silly because if you would do an engineering out, it's not negative, it's just a positive. Okay. So really you should flip this thing like that. And then you'll have a red thing going over here. Okay. But to get closer to an economist, I took the demand and I made it a negative number. Okay. So then it looks like a demand. That's all I did. You follow that? Yeah? Otherwise, I get these things on top of each other and it doesn't work. It's actually a nice picture if you think of it, what they make. All right? Okay? So that's why this thing runs down. And you will see that if I flip it, this little area will end over here, which is exactly what you want for the kinetic energy, right? Okay, now it ends up on the left side. Okay? You're gonna wiggle this thing a little bit, all right? Okay? So here's all your ingredients. Now this is the excess demand. By that I mean that's the excess that this guy is demanding over what this guy is supplying, right? That's what we call the excess demand or excess supply, I guess, in a positive direction. All right. And if I take the mutual elasticities and add them, I get something called the mutual elasticity. This is a little bit tricky because the elasticity is 1 divided by the mass of D, and this is 1 divided by the mass F. And then this should be 1 divided M total, right? Yeah. Okay. But if you've ever done the two-party problems, you know that this is super tricky to play. It's like putting inductors in series or in parallel. So, but when you express it as elasticity, it becomes a very simple summation. It doesn't get so complicated. This is also what is called the reduced mass. 1 over epsilon is equal to the reduced mass. Huh? So you can also call it the reduced. Yeah? I don't know if you've heard of that concept. Huh? Do you know about the reduced mass? Yeah, if you have 1 over m total, it's equal to 1 over m. What is it? V. 1 over m. Then this thing is the inducement. Now this is equal. They call it usually mu. Is equal to 1 divided 1 over m v 1. That's the reduced mass. You can look at it.
Same way as in electric circuit theory, right?
Yes. So it's a way of putting masses in.
Yeah. Same way they in electric
Yeah.
combine.
If you're an astronomer and you do all these planets that are moving, and you look at the center of mass, and then you see how these rotating with respect to each other, and then you use the reduced mass for the internal motion of the system. Okay, you can't use the total mass because that controls the motion of the center of gravity of the center of mass, right? So this is the thing, but when you work with elasticities, this is kind of more and more clear what's going on, I feel. So here's a picture. From the perspective of this inertial reference frame, the whole thing just looks like another momentum, but then using this reduced mass, this total inelasticity. Right? So it's almost like if you look at the inner interactions, you have a new elasticity that you can calculate this way. You can just use the excess demand in our spread, right? Okay. Do whatever analysis you ever did, right? Okay. That's the trick. Right. So what you want to do now is see that this P is this spread, that one goes, now doesn't change it. So that means these two prices are going to equalize, right? Okay. That means that the spread between how much you are asking and how much I'm bidding keeps going down through these interactions. Okay. That's what's happening here. Okay. I think you can apply out here. So you see that this is the decrease of the price of the demander. This is the increase of the price, but really increase this because this is a negative number, but whatever. Decrease of the supply. All right. So these inducements is a 1 times over a small amount of time. Okay. Now, if I multiply this one here, which is the mutual, desire to do the trade, the relative desire, okay, by the sheer amount of the extra demand, I get the amount of satisfaction both are getting. Okay? So this is the total amount of welfare that I'm generating, right? This is all the dissipation. This is how hot I'm getting. So you can see so much is going to the demander, that's called the consumer surplus. So much is going to the supplier, called the supplier surplus. Okay? Now, this force is going to be equal to V times V. It's always positive, but it goes in the direction of V. V is this thing, right? So this thing will go positive, but it will get smaller and smaller. So you'll see slowly you're dissipating down the surplus. All right? And in the end, you're just going to end up here, and then you're on equilibrium. Okay? Exactly what you see happening. And you imagine it as a system. All right? So this picture actually contains a lot of stuff. It contains Newton's third law, namely that this thing is equal to that thing. Okay. It also says that the equilibrium is going to be when everybody is demanding, the central demand, the aggregate demand here, the same as the aggregate demand. So everybody is demanding at the level of the aggregate demand. And it also gives you an equation of motion in time for how these are changing. In fact, you can calculate it and you find that something like P naught is equal to minus V epsilon P, right? Yeah, because this is what it is. Huh? What is it like this? So it's an exponential decay. This has a rate. Because this thing is V divided by M, and that's just the damping rate. So you'll get some exponential decay, V epsilon P, of your P0. So here's P0, and we'll just go down like that. We know the solution, right? Function didn't, because he does have a qualitative force. He says that in here now, this is happening. And not only does he have that, he also has to realize that he doesn't have a spring here, because then he's not going to get equilibrium. He also has, the invisible hand acting here, right? Because what would happen if I replace this with a spring, right? Sure, it will go down, right? It will just go like this, and the thing, this will oscillate like that, and that one will oscillate like that, right? Okay? That thing will make a weird motion, okay? Never really settled. So if you have two trainers, you can model them in this way of the two-body problem, and then with a little bit of flipping and minus signs, you can create these type of pictures that remind you of what's happening in the in these kind of graphs. But if you get a little bit more, you also get the equation of motion. You know how long it will take to get within epsilon of that, right? Here, it's an exponential with decay because it's a linear system. And then this is a non-linear thing. You can also figure it out with some of the up and off thing. Or if you have a complicated interaction, you have spring, and I don't know what you can have in between here, right? You can also figure it out. Huh? Now, should you do this every time? The answer is no. Way better off to take some reference frame and then try to somehow everything with respect to this reference frame. All graphs do and everything else does. Right? Now you just close your eyes and you calculate and you figure out what's happening. You don't worry yourself too much about this. I feel there's more to say, because this was in the past, but it was a huge hang up. Once you figure it out, if you go like, oh, okay. So how many times am I going to use the two-body problem? Right? Maybe if you do, then you have a situation. But you got to see this is what they have in mind is a very special situation. You can have way more general things, but this guy has this price, but this guy has another price here. There's no reason they should, this thing is all there. Or if you have a storage in between, it's just gonna like oscillate a bit. I mean, this whole picture is not so useful anymore. This is really, I think this is what they have in mind when they draw these pictures. I mean, they're reason like that. It's a very special picture.
So they only work with two-body problem.
if they do demand, right, the theory of demand, they have all these other theories like aggregate demand, and then they have maybe an infinite body problem, you know. So if they, this is what they call wall-rounding demand, because they have a two-body problem only in one dimension. You can also ask yourself what happens if I have another dimension. So, and actually, I think I want to end this lecture with that. So suppose you now have two dimensions, right? So one way to look at it is that you have this situation here. So you have, these are, say, two goods. This is good alpha, this is good beta. I actually have here apples and bananas, A and B, and here I have fruit salads, right? Mixtures, different mixtures of apples and bananas. All right. Huh? So these are two different types of fruit salad. Huh? And what you have, so there are two different kinds of fruits. You can kind of see this equation like here is just that this one is that, and they're totally disconnected. Okay. So you have two of these demand situations, one for alpha goods and one for beta goods, and nobody's doing anything with each other, right? That's very similar to what you would have in Newtonian mechanics. So you have a velocity here, a momentum here, and they're related, right? And velocity here and momentum here, they're related, right? The only thing that's different is here, these masses need not be equal, but okay. But you see, it's very, very, very similar. What they thought, and these are just two what they will call our Marshallian, because Marshall only considered these single good things, okay? But then the guy, Morats, came along later, and he had multiple goods, and he said, well, it's not good enough just to look at one good. You have to look at multiple goods simultaneously in your economy, because if the price of coffee changes the prices of tea, and you have all these things called substitution effects, okay, and they all influence each other, right? So you got a huge amount of equations that all came down to something you could write like this for two goods, right? So that the demand for good A, these apples, depends on the price of apples, but also on the price of bananas, right? And this is the factor was mentioned. This is this elasticity. It depends on apples, but with this cross elasticity, the demand for apples is influenced by the price of bananas, right? Okay. So this is what we would call an inertia tensor. All right. So you have these rotating systems, So you know that if you turn if you change the momentum in one direction, torque, the thing may start rotating over another dimension. Because if you're not along a principal direction, it will, if you take a tennis racket, you try to rotate it like this, it will go in weird ways, right? Yeah? You understand? Yeah. And just flat space, you get the same thing if you don't take your orthogonal system. So you're rounding along here, but then you would think that this will be affected, but it certainly is, because you don't have an orthogonal frame, right? So you get these cross effects. Okay. So this is what they would call a Walrasian demand function. And if this is only one thing, you would call it a demand function. All right. So these are now vectors. This is a matrix. It's actually called a tensor.
Can we extend it to more than two products?
Yeah, sure.
Yeah.
Make a huge list, right? They will do it. Right? Yeah. Of course, you have in inertial matrices, you got three, right? But there's no reason, or five. You make up as much as you want. Yes. That's a good point. Right? I was wondering how much time we have, but let's just get going with this, and then we'll finish it off next time. I just sketch here what's happening. But the interesting thing is you can still calculate like the surplus or do anything you like, right? So what is the surplus? Well, now you would calculate it like this, right? So you use this vector notation. This is a column vector, this is a row vector. This will be a matrix. It's calculated like this, and this will be the total kinetic energy, right? Which is just the surplus. Right? No, we'll get too complicated about that. And this is just a real number, right? It's positive, right? Or non-negative. Yeah, sure, because this matrix is positive definite, right? So there's no way you're going to get kinetic energy, negative kinetic energy, right? So the positiveness of a mass implies a positive definiteness of this tensor, right? Okay. So if I go ahead and do that, so I take this and put it in there, and then I take that one, I get this expression, right? So here I recognize like the Walrasian surplus in apples, and here I recognize the Walrasian surplus in bananas. And here I get a little bit more surplus, right? Okay, because of that substitution effect. And when these are zero, these epsilon ABs, then now then it will just be a simple sum. Okay, and the substitution effect will vanish. So these, I like to call these the principal elasticities, and these are cross elasticities. And then the substitution effect, the price, you can measure it through the economic surplus. It just tells you how the price of apples and bananas creates another way to get surplus out of the system. All right? Okay. Now, because this is always positive, a real number, it's easy to show that this matrix can always be diagonal. That's the case, okay? I can show you that, but it means that you can sandwich it in between, rotation matrix and its transforms and blah, blah, and that such a thing always exists, and, so this requirement, right, means that I can find two fruit, salads, so that these things become zero. Okay? And the substitution effect vanishes. So what does that say economically? That is saying that you can, independent of what kind of Walrasian economy you have, you can always diagonal. Meaning you look at these baskets, and they're kind of the eigen baskets, right? So these are like kind of eigen, right? The eigenvectors. These are the eigenvectors of that thing, right? Okay. So this is an eigenvector, and this is an eigenvector, okay? And these are the eigenvalues, right? So this is an interesting point that under this kind of Newtonian framework, any Walrasian equilibrium can be reduced by an appropriate coordinate transformation. So going to a different basket of goods to a set of n Walrasian ones. So you become completely decoupled. Okay. Right? And this is a reason. They have something similar. They make an argument for this. They usually they want to show this is positive definite, but they never really come to show that therefore you can reduce every Walrasian for any number of goods into decompose it, along what we would call the principal actions, directions, and those elasticities are the eigenvalues, right? So of this matrix.
And what would be the sort of economic interpretation of those diagonalized reduced masses?
Well, that means that you can decouple those directions, and you can just work, you can cycle your way through to the alpha market and then look at the beta market separately,
Yeah, but like your reduced mass is now sort of a combination of two goods.
This is not necessarily the reduced mass. This is any type of elasticity.
Yeah, okay.
That's just
Okay, so it's decoupled it from a property of commodity to more of a market.
All this it also applies to this situation, man. You just take anything. Just take any demand. All this says is speed is n times speed. With any demand. It's with respect to another one and the reduced mass. You see, maybe I went a little too fast with the same way. It's just a different topic here. Okay. I just said I wanted to make a difference between Walrasian general or Walrasian equilibrium and simple Marshallian equilibrium. Because you see this thing, you look at this situation and you change this guy into a big wall, you let this go to zero, right? You will see that when this goes to zero, then the total elasticity just becomes this guy's elasticity and it's independent of the other one, right? So this whole problem then reduces again to, all right? So,
do the cross terms always have to be the same, or could they be different?
no, they got to be the same because of this. They got to be the same. Otherwise, it doesn't work. I mean, it's the same in an inertia tensor, right?
Yeah.
They got to be the same. Otherwise, if they're not, there's no way to keep this positive definiteness, right? You can't have negative simplets, okay? This is not possible. And why not? Because you don't want negative mass. So similarly, you don't want a negative price elasticity because what it's going to do is all of a sudden those laws won't hold anymore. So you won't reduce your price when you're demanding more. You will increase it or something, right? So the law of demand won't be valid anymore. You don't want that, right? You can make infinite profits, okay? So, So ultimately, this comes from conservation of energy, right? So you can't, and which is simpler, so you can't create infinite simple. So you've got to get this thing, to stay bounded and real and positive. You're stuck, okay? Then you're stuck. Now, finally, what you can do in the electrical analog is create this thing that's called a mutual inductor. So you see the electrical engineering price is represented by these magnetic flux lines, right? So the magnetic flux is precisely the price because the magnetic flux lines here, they maintain that current. Right? This is another demander. But this one has its own demand of flux. Well, not another demand, another goods. This is good one and good two, and it's one demand, okay, one agent. And because these magnetic flux lines cross each other, right, you see that the price of good two here starts influencing the price of good one and vice versa, right? Look, it's like a transformer. So in Kuhn's paper, this is how it's done. Mechanically, we would do it this way. All right. So what he does with it, and we'll get to that when we do that, you have two markets, one market for apples, all kinds of guys just trading in apples, another one for bananas, everybody trading bananas, very complicated. And there's one in the middle there that's a consumer that is active in both markets. He's going and he buys bananas and he buys also apples, right? Whereas the banana producers are just carry me the banana, right? Telling me the banana, what is it, the song, right? Banana boat song. They're just doing the bananas, and the apples are singing in the orchard. But you, as a consumer, you provide this substitution effect, this magnetic coupling, it's called here. Okay? So you have two circuits. You see, if one circuit has got all your bananas and the other circuit has got your apples, you can't just connect them because you can't add apples to a banana. All right? But you can link these circuits, you can, so you can't connect the circuits directly, but what you can do is link them through the magnetic coupling. That's called the price coupling. So different markets can interact with each other through price coupling, not through direct dumping of the goods in the dollar market. Okay? That's an important concept, you see. All right. That's taken care of by this, right? So you can separate the different markets like we always do. Cheese market is guys doing only cheese and this. They're all, what is it, horizontally integrated or something, right? So they're all going and trading in the same things. But when you want to vertically integrate, you want to go through different goods, you got to do this. Yeah? All right. So these are very nice results, you know. It just tells you with this kind of stuff, you can go ahead and start making some serious models because these are good tools. Otherwise, you're just always dealing in one good, right? There's a lot of goods. And then you can figure out questions of stability of the markets and all that kind of stuff. All right. So that's that point. Now you have these insights to see how in general you can do that. In the next couple of lectures, I want to go through some very specific examples of how we can, as second order systems, just in one dimension. So I'm not going to do much with this. This will come into play in the next series when we're going to look at this circuit theory approach, where we have different circuits, and then we start really building stuff with this theory. All right. Okay. So then we'll go over this next week, and then we can ask some questions. Okay. All right.